Okay, so now we're in the middle of medium access. Medium access, today only the first part. We should not cover everything, that's too much for one lecture. I hope you had a look into all this and you understood the main problem of why we cannot use the classical medium access schemes. And this slide number 3 shows it pretty good, that you see, okay, we have a setting similar to a local area network, classical Ethernet, but we have this problem of our signals, that we have this decrease in the signal strength, extreme decrease if you have a wall in between, and so the signal is okay only up to a certain distance. So you can say up to this point everything is nice. Well, let's assume it works as long as the signal is above a certain threshold. If it's below the threshold, well, it's noise, simplified. And the same is true the other way around. So for the other sender, and then we see, okay, there's a certain overlap where we can receive, for the receiver B, both signals, but, and that was the main point, we will never see the collision here, for example, at the sender A, because this collision happens somewhere in this range where the receiver B is, but we will not see the collision here, because the collision will only add a bit of noise to your own signal. That's it, but the signal is so strong, you will not hear this. That was the key problem here. Okay, and out of this problem, I explained hidden terminals, exposed terminals, so the problem there, and also near-far terminals. I said, okay, this is the basic problem in a wireless setting. And then we added an algorithm to our multiplexing schemes. And then we had space division, multiple access, frequency division, multiple access, etc., etc. So basically, we have our multiplexing schemes plus an algorithm. CDMA will be covered later because it's a bit more complicated. And if you combine this, then you can have schemes as shown here for the classical GSM network operating at 900 megahertz, that you have certain uplinks, here shown 124 channels for the uplink down here, and you have a downlink, also 124 channels. These bands are called paired bands because we have the same bandwidth for the downlink as we have for the uplink. Those systems were made for voice communication, which is symmetric. That was the key idea. Okay, but you could do the same not only in frequency, but also in time, and you can have whatever other combinations. These were the simplest schemes, and the bit more complex ones was this OFDM, orthogonal frequency division multiplexing. If we add a clever algorithm, then we have this orthogonal frequency division multiple access. Okay, what do you have to know about OFDMA? Definitely not more than I explained during the lecture. We will not go into the details for electrical engineering. For you, it's important to know, okay, we actually apply frequency division multiplexing, now using many smaller so-called subcarriers. How we create them This is Fourier transform, etc. We don't have to go into these details. It's a bit more complex, but now assume we can create these subcarriers, and then we distribute single users over these subcarriers. So we assign a subset of subcarriers to certain users. So user green in this example can use 3 plus 1 plus 2, 6 subcarriers somewhere. User red can use 1, 2, 3, 4, 5 subcarrier. So that's the idea. So we separate users by using different carrier frequencies. Now, small subcarriers with a carrier frequency. So we distribute those users over different subcarriers. Plus, we actually can send the data of a single user using several subcarriers. Has many advantages, especially if you have narrowband interference. Assume you have interference somewhere in the spectrum, killing parts of the green user, so this subcarrier, you still have enough subcarriers to survive, to receive the data. You always apply forward error correction. So that is the idea here. So at least you heard the term OFDM without going into the electrical engineering details, but this is technology used in the new Wi-Fi's, LTE, all the 5G technology, then also the digital television, digital radio. Also your DSL router uses this. If you look this up on the web pages of your router, you will see the so-called spectrum that is used over the telephone copper wires. So this is a well-known technology, heavily used now. Okay, so to the questions, and please again do ask whenever you want to ask anything. So you have to know what is the main reason why the MAC schemes do not work, and why do they work in wired networks? Well, don't you have attenuation there as well? Why don't we have the problem in wired networks? Or do we have the problems? Does anyone know what is the difference? We have attenuation also in wired networks, in wireless and in wired. But why don't we have hidden terminal problems in wired networks? Okay, one of the answers is in wired networks, one station transmit, all others will receive. Attenuation is way bigger in wireless. So the problem indeed is the attenuation is much, much higher in wireless networks. Think of this d square or to the power 3.5 to 4.5, extreme strong attenuation. That's one factor. And the other factor is there's no length limit in wireless networks. In all wired networks, so if you go to a classical Ethernet or to whatever wired networks, there's an upper limit for the length of the cable. So for today's wireless, for today's LANs, not wireless LANs, today's normal fixed wired LANs, the upper limit is something like 100 meters. So there's an upper limit. And using this technology and, well, obeying this upper limit, you can make sure that all the stations connected to this cable will receive the signal strong enough. That is the problem. So I showed you the example on slide 3 that you will not be able to receive the collision. And the classical fixed Ethernet had also a maximum segment length, as this is called, for example, 250 meters. And within the 250 meters, the signal was always strong enough and all the stations could hear the collision. That's the idea. And here we don't hear the collision. That's our main problem. So You could limit the range of a wireless network by, I don't know, painting a white line on the ground and saying, okay, using the Wi-Fi, you're not allowed to leave this cafe or whatever. But how can you make sure that there's no one outside also using the wireless LAN, creating exactly this hidden station or hidden terminal problem? Yeah, that's a problem. Okay, so FDMA complexity compared to TDMA. What do we need if we apply FDMA? Think you are the receiver. And now we use FDMA. What is one of the problems we do not have in TDMA? Right, agreement hopping pattern. So even simpler, you have to know the carrier frequency. So if you do not know the carrier frequency, what should you receive? You could receive everything. Yes, today's devices, they can have some kind of a broadband receiver and then they pick the right frequency, but that makes systems way more complicated. That is expensive. So you're fully right. If we start hopping, then you have to know the hopping patterns. You have to know the frequency, and you're right. We have to distinguish the signal from noise. So is this noise? Is this a signal? So before we can apply FDMA, we have to agree upon frequencies. For TDMA, it's not necessary. You simply listen to the medium and then something arrives. There's data. That's it. Exactly. Another answer is different antennas for different frequencies. So yes and no, it depends on the frequency range. So for example, you can use a 900 megahertz antenna also for 1800, also for 1900. Maybe it's not as good, but it works. 900 and 1800. Why? Because this is just twice. So 1800 is, 2 times 900. And 1900, that's almost 1800. So, okay, but it works. But it's more difficult to use the antenna for the 2400, for example. This is why we usually have different antennas for the mobile phone networks and the wireless LANs built into our smartphones. Then another answer is also modulation, right? You have to know, in addition to the frequency, also the modulation. But to be honest, for TDMA, you also have to know at least the bit patterns, the coding, etc. But it's true. So FDMA, this is a more analog thing. You have to know frequencies. You have to tune into frequencies. That is absolutely right. Okay, a more general question is, who is actually responsible for medium access control if we consider the whole frequency spectrum? In chapter 1, I explained a bit about frequencies and how frequencies are used, who's doing what in the spectrum. But who's responsible now for which part of the spectrum? And there is not a single answer. Who is doing medium access control? Who or what? ITU, right? ITU is one answer. So indeed, ITU actually plans in the so-called World Radio Conferences since more than 100 years, plans what we do in which part of the spectrum. So this is for analog radio, this is for cellular networks, this is for this, and this is for that. Next answer, right, authorities. So the authorities then within the spectrum. So if the ITU says this spectrum is for, let's say, cellular networks, then authorities in Germany, Bundesnetzagentur, then decides, okay, via auction, for example, that network operator T-Mobile gets these frequencies and Vodafone gets this, and Telefonica, we only have 3 operators, gets this part of the spectrum. So that's the next step. Then within this frequency, so a Telefonica base station or Vodafone base station, whatever, then the base station has to say, okay, I'm using these and that frequencies for this cell or for this sector, for example. Then another answer was the wireless LAN administrator. Yes, you at home, you can decide which frequency to use for accessing the medium. But then, within this frequency, your hardware decides when to access on this frequency the medium. We will learn how this works for wireless LANs. But so in the end, it depends on where do you look at, which part of this hierarchy. We have the whole spectrum, and then we have the ITU, we have the national authorities, and then we have companies, we have different technologies, and in the end, there's a piece of hardware that decides I'm using this frequency now. And we will learn how this works. So you see, there's not a single answer, but you should be aware of these different components and actors, authorities operating here. Okay, so we also looked in this duplex. How can we do duplex in wireless networks, and how is this done in wired networks? Duplex was sending in both directions. So you can send from A to B and from B to A. And if we can do it at the same time, we call it duplex or full duplex. If we can do it alternatively, it's called half duplex. And if we can send only in one direction, it's called simplex. So how can we implement this in wireless networks, this duplex? And how do we do this in wired networks? Different frequencies, different channels for up and downlink. That's the classical way. So the classical way is FDD, frequency division duplex. So this is a good idea if you roughly know the percentage of traffic going downlink, the percentage of going uplink, because then you can assign a certain spectrum to the uplink and to the downlink. And for the classical voice channels, well, we know from history that typically each person is talking for 40% of the time and 20% of silence. So this is symmetrical. And this is the reason why we have the so-called paired bands, where we have the same bandwidth for the downlink as we have for the uplink. Today, this is not always a good idea, because can you imagine why we don't have, maybe we should not use symmetric up and down links? Any ideas? Think of the traffic characteristic. Exactly. We download way more than we upload. Yes, we watch video, 99% receiving, streaming, bursty traffic. Exactly. So it's highly asymmetric today. So this is why we need way more for the downlink compared to the uplink. Again, look at your DSL modem. You will see we have more spectrum for the downlink compared to the uplink. But with symmetric paired bands, we cannot do this. So that doesn't really fit. So this is why today we use different technologies for the downlink, squeezing way more bits per second into our tiny spectrum compared to the uplink. That's one way of doing it. Plus, we can invest more energy in the base stations. So we can push more bits through the channel compared to your mobile phone, and you don't need it. And then you also wrote bursty traffic. Exactly. Additionally to this asymmetric usage, we have highly bursty traffic. That means you click on something and then you need a lot of data. Or you start streaming, and in the beginning of streaming, the system really pumps a lot of data to your device so that you get almost from the start a high resolution. You notice in the very beginning the resolution is not as high, and then the resolution gets better and better and better. But actually zapping through channels, streaming channels, really puts a lot of stress to the system. Because if you start streaming and you stay with the channel or the stream, that's really a piece of cake, because that's not that much data. You just download some of the initial frames and then some of the deltas and some frames from time to time. So that's not a big problem. But zapping through different streams, that's one of the problem. And also browsing the web, that's very bursty traffic. In wired networks, duplex. Do you know how this is done in wired networks? Well, DSL is one answer, but a very simple answer. Different wires, right? So the phone network you use at home, the classical phone network, has 2 wires. So it's full duplex using 2 wires. But inside the network, the classical network uses 4 wires, 2 in each direction. Well, you need 2 wires for the current to flow. So that's laws of physics. But there exactly you have 2 wires per direction. So you can split this. And something similar you can do for local area network, gigabit local area network. If you have 8 wires, you can use 4 wires per direction, for example. So you do actually space division duplex. So you see, space division can also be used for the duplex. What I've shown the slides are only examples. You can mix this. Okay. So now, nasty situation. Assume all stations can hear all other stations. So everyone can hear everyone else. So no one is hidden. Now, one station wants to transmit and senses the carrier idle. It's idle. And why can a collision still occur after the start of transmission, although the medium was idle? I will come back to to the other questions in a second. So now assume you hear everything is idle. Okay. So you know it from fixed networks. Exactly. So if 2 send more or less at the same time, the signal still needs some time to travel. So 30 centimeters in 1 nanosecond, it still needs some time to travel. So that is one of the problems. Exactly. So the receiver can start to transmit idle wire or idle medium before the signal reaches this receiver. That's true. So all the answers are correct. Okay, and in this context, before I come to the other question, is also there are situations when this problem of hidden and exposed terminals cannot really be solved. We will come back to this in the final part of this Q&A. But for now, you're absolutely right. So here was the question. Why can't you use one medium with one frequency for both directions? Well, the point is, you're right. So you can use the medium, either space for wireless systems or a wire on the same frequency for both directions, because, as you wrote, exactly, you know what you send. This is exactly what you do in the classical digital telephones, ISDN, whatever. This is called echo cancellation. So you know what you send, and while sending, you will receive the signal from the other side plus the echoes of your signal. This is something similar you do when you use video conferencing with audio signals. The computer knows what you send to the computer, your voice, music, whatever, knows the receiving signal and can then subtract your own signal from the received signal, to avoid these echoes. But this requires that you know where the echoes are. You can automatically measure this. So your idea works, and it's called echo cancellation. Why don't we do this in wireless systems? The point is, when you send your signal, you have an output power of, let's say, something like 10 milliwatts. The received signal from the other side is something like picowatts, attowatts. So that's magnitudes weaker than the signal you send. And then the problem you have is in your so-called low noise amplifier. That's the hardware that actually receives the signal and amplifies it. You will not be able to detect anything from the received signal from the other side, because actually your own signal is that strong. It will simply drown out all the other signals. And that's the problem. So your own signal is 1,000,000 or 1,000,000,000 stronger than the other signal. So although in today's systems you use different frequencies for sending and receiving, your mobile phone will not send and receive at the same time. Because although you send on a different frequency, your own signal is that strong, your receiver is a very sensitive one, and this receiver cannot receive anything, although it's a different frequency, because we do not have perfect hardware. So although we use a different frequency for receiving compared to sending, we avoid sending and receiving at the same time, because the sending signal is that extremely strong, and we use the same antenna for sending and receiving, and we electronically switch between the sender and the receiver in our device. And we do not want to send and receive at the same time, because our sender is way too strong and our low noise amplifier would not be able to receive anything. So that's a rather technical problem we have. But in theory and in wired system and for audio, you can do exactly what you wrote. You can send and receive on the same frequency at the same time, because you know what you send. And if you know the echoes, you can subtract the echoes and your own signal, and you will have the original signal. This works if your signal and received signals are roughly have the same strength. Well, maybe by the order of 10 weaker or something like this, but not a factor of 1,000,000 or 1,000,000,000 weaker. And that's the problem in wireless systems. This is why we cannot do it. Okay, so these are the problems we have. And now I explained a bit more about possible solutions. And the interesting thing is, the very simple scheme with Aloha or slotted Aloha is exactly the scheme we use also in today's mobile phone network for the initial access of the medium. Because if we do not coordinate anything, that's the only way to go. I mean, what can we do? If we have no coordination at all, then Aloha or slotted Aloha, so we at least have some clocking. So we're synchronized. That's what our mobile phones are. That's all we can do. We cannot do anything else. So, okay, after explaining this, I went through different other schemes, and they all have something in common. All the other schemes that they usually have, like this one, a reservation phase, for example, organized by slotted Aloha, and then a phase where we can transmit the actual data. That's way longer. And the idea is that maybe we have collisions during this reservation phase. But if we are successful, then the transmission will be successful, the transmission of the data. That's the key idea. So all the schemes I explained then, they use these two phases of reservation and then transmitting. And also the scheme you can use in wireless LAN, this MACA, has these two phases. You have a reservation phase using this request to send, clear to send, where you can have a collision during the request to send phase. And if you're successful, then you have your longer data transmission. That was the basic idea there. Okay, and then we also went through some polling mechanisms, polling that's similar to USB. So the basic medium access for TDMA, this is typically TDMA schemes or combined TDMA FDMA schemes, they usually have a reservation phase and then the access, well, the transmission of the data. But you can do this only if you have some kind of coordination, because someone has to tell you if the reservation was successful. Without this, well, you cannot do anything but Aloha or slotted Aloha if you have at least kind of a time synchronization. Okay. First of all, are there some general questions to these types of medium access? If not, we go to the first question. Hidden exposed terminals. Recall the problem. It was exactly this, okay, I do not hear the other and I start sending. Good question. Do we use Aloha nowadays? Yes. We use Aloha, a very simple Aloha, exactly in our wireless LANs, if the medium was idle for a longer time. So, if nothing is going on in our wireless LAN for a longer time, we will learn how long longer is when we come to wireless LANs, then you can have an immediate medium access. So, just access it. So, and this is exactly Aloha. Or who else is using Aloha? Discussions among humans. Well, oh, it's silent, I start talking. So that's Aloha. The problem is, can be, yeah, you're right, the problem is right. Can be lots of hidden stations. It needs a long time. Yeah, if we have exactly this issue, okay, we use Aloha and we have the satellite constellations. Then, indeed, you can start sending. We have these problems of hidden stations, but it takes a longer time before you notice that something went wrong because the collision is at the receiver, which is the satellite. And this is why, if we use Aloha, we need some kind of acknowledgement mechanism. For discussions, well, you notice this. Well, you start talking, someone else starts talking, oh, collisions, you stop talking, or there's a moderator. For satellite networks and also for our wireless LANs, we will see that wireless LANs use acknowledgements. And if you do not receive an acknowledgement, this means, okay, something went wrong. We'll come back to this when we discuss wireless LANs. So hidden stations indeed is a problem. So now one thing is you wrote, that's perfect, that's right, a lot of hidden stations, but reservation Aloha and MACA should not have this problem. Okay, so you're right. That was, okay, let's jump to the last question. How can MACA still fail in case of hidden and exposed terminals? You should not have the problem, but what happens if you have mobile stations or changing transmission characteristics? The problem is exactly when stations move, you exactly have this problem what you wrote. Suddenly you have a good connection or you don't have a connection at all, or you move into the transmission range of another station. So the transmission characteristics, they change over time, and MACA only works if it stays the same. So usually, yes, it works, but if you have a lot of mobility or people moving in and out these transmission ranges, so you have absorption, a lot of attenuation for your signals, the transmission patterns, they change over time. And this might MACA, well, the operation might not be perfect. Sometimes it will work, sometimes it will not work. So it's not the 100% solution. For example, when we set up a wireless network in our building using more than 400 nodes for sensor networks, we experienced that more than 70 of the connections were only unidirectional. So that means only one device could send to another, but not the other way around. So MACA wouldn't work at all in this setting. And to make it even worse, these 70% were statistically distributed over the stations. So they changed over time, and only some of the connections were bidirectional, symmetric connections. So it's quite common that those links are asymmetric. You have unidirectional links, so that you can send only from one station to the other, or that means you can interfere another station, but you will not notice anything. Why does this happen? Well, because real systems are not ideal. So for symmetric links, you need actually a perfect setting with identical hardware, sender, receiver hardware. But you have different antennas, different receiver characteristics. So the power amplifiers are different, the low noise amplifiers are different. So you have different characteristics for receivers and for the transmitters. And so these are the real world problems. So moving devices and real asymmetric hardware, so to say, these are the problems. So exactly. So now we answered already the last question. Okay, coming back to the first one, hidden exposed terminals. What happens if we use Aloha, slotted Aloha, reservation Aloha, or MACA? MACA, you answered already. Well, MACA solves exactly the problem of hidden and exposed terminals, assuming certain transmission conditions. Sure. So, what about the normal Aloha? And you have hidden terminals. What happens? Does Aloha care about exposed terminals? Come on. Aloha and exposed terminals. Well, exposed terminals means that you less listening to the medium and you care about the medium. But for Aloha, you're absolutely right. No one listens to the medium before sending, so there are no exposed terminals. But hidden terminals, yes, that's one of the big problems. Yeah, sure, you can have hidden terminals. That was, by the way, when I explained Aloha, that the origin, Hawaiian Islands, that's one of the problems there. If you send from two islands to one of the central island of Oahu, then in Oahu, on the antenna there, you can receive the signals from, for example, Kauai and Big Island. But those islands, the senders, they're hidden from each other. So that's one of the problems. You have high volcanoes in between and all these things. So this is where actually Aloha comes from. This is also the reason why it's called Aloha. So slotted Aloha doesn't really make it any better. Slotted only means that you are allowed to start sending only at certain points in time. But you have the same problems of hidden terminals and you do not care about exposed terminals. You're absolutely right. That's exactly the same. Okay, and what happens if you do some kind of reservation? So Aloha during the reservation scheme and then a second phase with the reservations. What happens there? Assuming non-mobile stations. Do you solve the problems? Yeah. So absolutely right, you send only in the reserved time, and all the others, they have to wait, because all these types of schemes, they come from satellite technologies, and there the satellite sends down some kind of an allocation vector to all the others. That means all the stations should receive this. You have always this first phase, competition, and then maybe there's a collision up there at the satellite. The satellite sorts out everything and sends back a vector that tells all the stations if they were successful or not. And if you were successful, then you can access the medium, and you can be sure that no one else is now allowed to access the medium. So that's the idea. Okay, so now TDM patterns compared to random demand-driven TDM. So for TDM, we have different systems. We have systems that have kind of fixed patterns. So every 10th slot, you can transmit 100 bits, for example. Or you have demand-driven TDM. So a wireless LAN is typically a demand-driven time division multiplexing scheme, because if you have the demand to send something, you try to access. How we will cover in the chapter about wireless LANs. But there are other systems that use fixed patterns. So what scheme is better and what case of traffic patterns? Fixed data rates, varying data rates. And then we come back to phone systems and computer networks. And then you see one of the big problems of today's networks. What scheme is better? Fixed pattern can be very simple, right? Because you know every whatever 4.165 milliseconds you can send something. And for what type of traffic are fixed patterns quite good? Fixed traffic generated by classical telephone. Yeah. So the classical ISDN telephone, for example, generates a permanent fixed data rate of 64 kilobit per second. Okay. And then we know if we compress this, etc., then we can easily squeeze this into a repeating pattern of time slots. That's the classical scheme we use since many decades, TDM schemes in telephone. This even worked for analog phones. Fancy thing, but it worked. Demand-driven, that's classical computer networks. And if you keep this in mind, that the classical telephone used this fixed pattern, fixed TDM, computer networks, this more demand-driven. Now I click on the page, now I have to transmit something, now I download something. Then you understand also the shift in the mobile phone systems. As you will learn in chapter 4, we started with GSM, fixed patterns, mainly geared towards voice traffic. And then suddenly we have this computer-generated email, whatever, messaging, all these things, video download. This is not a fixed data rate. And what happened to our mobile phone network? This is why we explain GSM, GPRS, then UMTS, then LT, what we have today in the next chapter. And you see exactly this change of the traffic patterns reflected in the technologies. Okay. So, benefits of reservation schemes. Well, we partially answered this. But maybe still interesting, we do have collisions in phase 1. So, what do we win? So now we don't have collisions during transmission of the real data, but we have collisions in the Aloha phase. But why is this still a good idea to do this? Why do we benefit? Why do we benefit from these schemes? Because we still have collisions. So why not sending the original data in the first place? Lower collision rate, yes. Why do we have a lower collision rate in this first phase, in this Aloha phase? Yeah, you don't lose the actual data. Yes, the answer exactly is reservation packets are small, very short packets. Yes, exactly. we transmit for way longer time. So that's exactly the idea. So the reservation packets are way shorter. Those RTS, CTS packets, for example, or those short Aloha slots. These are short slots, only some bytes, maybe only a single byte. That's the basic idea. But the data, the original data we transmit, that's way more. That's then whatever, 1,000 byte, something like this. That's exactly the answer. Okay, that sounds good, but what are the disadvantages? Disadvantages of the reservation schemes compared to, for example, Aloha. Waste of time, latency. Yes, you answered already. Yes. So the problem is you first have to perform the reservation and then you can send. So if you have only a low load in your network, this is waste of time. So, what is better? There is no clear answer. It depends on the current load. And this is why wireless LAN, for example, does not use the reservation mechanism under normal circumstances. Only if you have high interference, it can go to this MACA, this RTS CTS scheme, to avoid this interruption of the data transmission. So the problem with the reservation schemes are always you have to wait for reservations. So for spontaneous transmission, reservation schemes are not the way to go. But you might have the problem that you have a collision with the original data. Yes. So that's the problem. You see, there is not always a yes, no, black, white answer. So the correct answer is always, well, it depends. But then at least you should be able to answer, it depends on what. But it depends. Okay, so we went through all the questions. Are there some more questions from your side? Just think of it for a minute. So I've put the new material in the net, and next time we will cover the remaining part of this chapter 3, and we'll start then with GSM and telco networks. But there's a question. Okay. One question related to GSM. You can call emergency service without a SIM. Yes and no. First answer is yes. This was the case. In many countries, they stopped this because right before Christmas, we had a lot of abuse of the emergency calls by the kids. Oh, I got a new mobile phone. I don't have a contract, but let's try it. Oh, 112 is the only number that works. Oh, let's try this. Oh, hi. So some countries stopped this. But it's true, it should work without a SIM. If they also get the higher access class, you could use that to run a denial of service attack. Exactly. So emergency services can be used for denial of service attack. But the point is, the police knows which mobile phone this is. So you need anonymous mobile phones. That is important. Okay, so with the normal phone, don't do this because the police knows you and the mobile phone. And this is why usually you don't get a mobile phone without personal ID. So the operators want to know who you are. You can steal one, etc., etc. We know all this. So if the phone can switch the access class for calling emergency, can we manually do that with an SDR, for example? Yes. So there is no encryption, there's no secret. Look up the standards called GSM 02.11. The access classes are defined there. And then if you know the channel that sends out these access classes, and you could fake this. Yes. So this is not a robust military system. No. So you could do a denial of service. So that is indeed one of the problems. And you have similar schemes for the packet switch network part in GSM. I will come back to this in chapter 4. But this is not a high security system. Okay, then there was a question, how did this fact change mobile phone system? Which fact? That I can attack it, or that the emergency calls now block this? Question 2. I don't know which is question 2 now. I have several. TDM. The advantages. Oh, okay, I understand. The question 2 here on the slide, sorry. How this fact changed mobile phone systems. Okay, the fact that we now have more and more computer-generated traffic. Well, indeed, we have way more computer-generated compared to human-generated traffic. Changed the mobile phone network in a way that today we do not explicitly support voice any longer by having kind of symmetric paired bands, but this is all data traffic, and we more or less build up the new mobile phone networks in the systems that they mainly support computer-generated traffic, and then there are some additional humans using the phone network to talk to each other. But it's more and more a network for computers. So it's more this classical, what we say, internet traffic, bursty traffic, heavy tail distribution, whatever it is. So we have a lot of short transmissions, some longer transmissions. So, and that's completely different from the distribution you have with normal voice calls. Yeah. So this is the major change, so that you see that today's mobile phone network following 4th generation, they do not have the classical phone network in its core anymore. So the core of the 2nd and 3rd generation is still the classical digital telephone network geared towards voice. From the 4th generation on, voice goes over IP, voice over IP over LTE. So that means voice is nothing but an IP packet. Yeah. So that really changed. Okay. Some more questions. Okay, as always, you can send questions by email, so I can integrate it the next time. If there are no more questions, I have to thank you all for today, and I wish you all a nice week, and we see each other, hear each other next Wednesday. Exactly. Aloha. Bye.